Hello, everyone. We're back again in the quantum track. We just had a talk by Bob from Cambridge Quantum, and right now we have Sasha Lazarevic doing an overview of quantum computing today. So, Sasha, can
Hi,
hi, Sasha.
Milos.
How are you?
Hi, everyone.
Thank you very much for joining us. So I'm gonna let
Thank you
you
for having me
do
here.
your talk.
Okay, great. Well, excellent. So, um, yeah, I can see that my slide is already there. I hope I can control it. Yeah, so, um, well, you have heard already about quantum computing, and there is a lot of discussion about this, a lot of talks, a lot of interest in quantum computing, and also some other quantum technologies where quantum computing is just one of them. First of all, uh, I wanted to remind or to mention what are the underlying principles and what are these quantum phenomena that we are trying to exploit in quantum computation. So 4 of them, as you can see on this slide, superposition. This is magical phenomena which is happening on this level of quantum systems and the particles like photons, electrons, where uh, these particles they can be in a charged state. They can be also in the state which is not charged, but uh, they can be also in a state which is a kind of uh, two states at the same time. Well, if I can just simplify it like that, or to be more correct, to be in a linear superposition of these two states, which is just indicated here on the left-hand side of my screen. Here you see several qubits. And if it is just a basis state, 0 or 1, this vector will point to the north or the south pole. Here, this vector is pointing to any point on the surface of this sphere. Uh, and this is actually the phenomena that we are trying to exploit to encode much more information in a quantum computer than we can in a classical non-quantum computer. Uh, and you will see later, well, this is basically one of the basic premises why these quantum computers, they are so powerful. Then the next phenomena is entanglement. We can put two quantum systems in a kind of perfect correlation where even though if they are distant one from another, when we manipulate with one, then the second one is performing the same kind of behavior. It's following the first one. So, and this is also a phenomenon that we try to exploit and in order to introduce a parallelism. So we can manipulate with multiple quantum states at the same time. Then there is quantum interference. So here you see, for example, that if I take this unitary matrix and I multiply it with this vector, and this vector is actually probability amplitude vector, I will get another probability amplitude vector where these values are changing. So 1 is going down and 0 is increasing. And if I apply this unitary matrix twice, so I just apply it twice, then this probability amplitude vector is evolving. So uh, this probability is increasing, and this here upper one is just going to 0. So this is the interference. We are evolving the system, our quantum system, towards the expected result of our calculation. And then the fourth very important phenomena is measurement. So all these quantum systems, they can be superposition, they can be entangled. But if we want to see what is inside and what is this state here, where is this vector pointing to, then all this magic is disappearing and the quantum state just collapses. It becomes either 0 or 1. So in order to understand where this vector was before the measurement, we have to repeat our circuit or our experiment many, many times, 1,000 times, 10,000 times. And then as the result, we'll get to the probability distribution. So this probability distribution, it is telling us what was the state just before the measurement. So these are four quantum phenomena that were discovered quite time ago. There is a mathematical framework which is called quantum mechanics behind it. Why this is happening, nobody knows, but we have some mechanism how to describe it. And also with quantum computers and other quantum devices, we have a mechanism to exploit it. So when we are talking about quantum computing, it is just one of them. There is also a host of other technologies like quantum sensing, communication, simulation, annealers, etc. And here you can see quite a lot of interest in sense of government spending, investing. So these numbers here, they look really quite high, but I think these numbers are actually, we need to just know that there are commitments, government commitments, for example, China, 10 billion. So it is not every year 10 billion. So it was announced a few years ago, and this is for the period of 5-10 years. But also there is a lot of interest among the private investors. For example, in the United States, a lot of private equity is investing in private companies. For example, this year, just Psy Quantum got $450 million in developing a photonic computer. And if you want also to invest yourself, there is the first company that went public, IonQ. They are listed, so if you want, I mean, that's I'm not recommending anything, but it just shows a quite high interest for all these different technologies. So what are these? Quantum sensing is maybe the most mature of all. There are already some devices. We know about atomic clocks. They are there since a long time. Well, basically, this atomic clock is exploiting quantum phenomena. But they are very expensive. They are huge. So there are some interesting projects like this one here, which aims to create some ultra accurate, mass producible, portable devices, small size that can be used for some network devices. Then quantum gyroscopes. This is very important for the future cars because they can, using these gyroscopes and accelerators, quantum accelerators, they can identify exact position of this car without relying on satellites, on GPS, which is very important for some navigation, autonomous car navigation systems, especially also indoors. And then we have also these gravimeters. They are very precise. They are used for seismic and volcanic research, for the oil reserves exploration, looking for underground water, and also in construction. So a lot of things happening. For example, another application of quantum sensors, this quantum radar is coming from China. It's can detect stealth bombers, stealth aircrafts by just using much weaker signals than traditional radars and being much more precise. Then quantum microscope. This here we see a Swiss startup company, QNAMI. They are producing microscopes for the analysis of magnetic materials at the atomic scale, and also quantum life science in the sense that all these quantum sensors, they are improving scanners, magnetic resonance imaging devices. They can better detect cancers, inflammation, different processes in the body. So it's there is a lot of purpose. Just here talking about quantum life science, I want to say, don't believe in quantum healing and quantum wellness and these things. So that's not really. I mean, it doesn't really use this quantum phenomenon. It's just some kind of scam. So next important technology, quantum communications. So quite a lot of interest in quantum communications to secure the communication, because here, for example, you see the difference between classical and quantum communications. Here you have Novak Djokovic. He's a very good player, so he's hitting these balls very fast. But you can imagine a hand that is capturing these balls and somebody's reading these numbers here and then sending further these balls. And so you have somebody intercepting your communications and you don't notice it. With quantum communications, it is different. You imagine these soap bubbles. If there is a hand trying to capture, well, it just collapses. It collapses like our superposition. It explodes. It's no longer there. And using the no cloning principle of quantum mechanics, nobody can recreate exactly these soap bubbles or the pieces of information that we are sending over the channel. So it is very useful in exchanging decryption keys. So here on the left-hand side, you see how it works. And this is basically known as quantum key distribution. So we use the secure quantum channel to exchange the keys. And then afterwards, this is symmetric key exchange and symmetric encryption, so this is not vulnerable to Shor's algorithm. So in that case, we are safe, and even afterwards, we can exchange the messages, encrypted messages, without worrying that somebody will be able to decrypt it. There is also another group of use cases is based on super dense coding and quantum teleportation algorithms. These are algorithms, when you start learning about quantum information science, these are basic algorithms, and they show actually that you can save resources. You don't need 2 bits. You would need just a state, one quantum state, to communicate the information. So it's the idea is how to compress your communication protocols, how to reduce the resources needed from the for the transmitting the data. And also another very important use case of quantum communications is building quantum network. So we want to be able to interconnect quantum computers. And there is a lot of experiments, especially successful. They were in Netherlands the last several years, that a group of researchers, they managed to actually to create to entangle quantum systems remotely without any direct communication. So this is fascinating, and there is a lot of work being done in this field. And also, this also coming from China. This year, they have completed first integrated quantum communication network over a total distance of 4,600 kilometers. You probably remember the satellites that were launched already 5 years ago. And in meanwhile, this terrestrial network, communication network, has been built. There is a new technology actually which extends the limit from 70 kilometers to over 500 kilometers of the one quantum network link. This is important because after this limitation, well, actually you need to perform the measurements, you need to recreate, well, to encode again your message to send it further. So if at this point can be weak point. If somebody has installed a malware, then basically you can secure everything, but this can be the entry point for the hackers. So they have used this twin field QKD, and now it's much better than the previous version. They continue working on this technology together with research groups from Austria, Italy, Russia, developing also some new generation of satellites. Then we have quantum annealers. So this is based on superconducting qubits. And this company, D-Wave, they have started producing this already some time ago. The Advantage chip, it has more than 5,000 qubits. But this is not a really universal computer. You can't develop a code. You can't run a script, for example. What you can do is you can use it for optimization purposes, like, for example, logistics, supply chain management, etc. And it's quite popular. There is a lot of people who play with this. They can resolve real problems. The thing is just there is a quite a strong debate among the researchers if there is a proof that there is a quantum advantage for using these quantum annealers. Yeah, so that's basically how it works. Well, that's these superconducting qubits. They have a grid structure. They call it chimera. So, and this grid structure is very, it's equivalent to Ising model used in physics. So basically, your optimization problem you are going to convert into the Ising problem, and then you are going to implement using D-Wave routines on their chimera CPU or QPU, and then you're going to slowly, adiabatically, to evolve the state of the energy of this processor until with quantum tunneling, that's another phenomena, actually you will reach the optimal state. So you're measuring and you get the result of your optimization solution. And we are coming to the universal quantum computer. So universal quantum computer is actually what we are looking for and what we want to exploit to resolve world hardest, most difficult problems. So how does it look like? Here you see the logical architecture. So you will represent your problem mathematically. Based on this mathematical representation, you will develop the algorithm in some of the high-level programming languages like Python, using some libraries there. Then um, your code is going through the transpiler. This transpiler is optimizing the code and preparing it to run on the underlying hardware, because the topologies can be different, or the underlying hardware can be different. Then there is a compiler. It is going to compile your code into assembler, microarchitecture, and in the end, it's going to be converted into analog instructions that will be executed on this quantum processor. So you see that all these layers here, they are actually run on a classical computer. And only the last one here is the quantum processor, or the qubits, as we call them. So when you are developing your algorithms, you need to follow certain syntax. And this syntax includes quantum gates or quantum operations. So here you see just a subset of them. The real set is larger. Here we have a bit flip, for example. This is the way how we can represent the states. And then when we apply this bit flip, this vector will point down to this number 1. Hadamard will create superposition. The C naught will put 2 qubits in an entanglement. This measurement will help us to get the result. And actually here we can see how it looks like visually on a quantum circuit. These are 2 qubits here, and then it goes from left to right. So here we have Hadamard gate, C naught, measurements, etc. And then these here, double lines here, they represent bits. So the result of our computation is a bit string here from these 2 bits. Yeah, so the way how you basically design, so how you how you build your algorithm is you want to exploit superposition to keep more information in quantum states. And here you see that, for example, with 50 qubits, you can represent 2 to the power of 50 bits, or 128 terabytes. So with 2000 qubits, well, you can imagine, I mean, this is 2 to the power of 2000. It's very, very large number. And then there is a problem, actually, how do we load so much information, so much data into this 2 to the power of 1000 or 2000 states? Yeah, this is a complexity, but that's why this universal quantum computer is so important, because in many of the problems, actually the space of the solutions is increasing exponentially, and this is allow us to generate these different solutions on the fly and to keep them in our composite quantum state in our quantum processor. So once when we have these states in a superposition, then we are going to exploit the entanglement to parallelize the operations. Then, as we have seen, using the quantum interference, we are evolving the overall state to get expected results. And then we have to measure multiple times in order to get the probability distribution of these results. So the result is always probability distribution. If the result is exact, then just one value is going to have probability 1, and all other values, they are going to have probability 0. But what we are getting is the probability distribution. So what do we use actually as underlying hardware? So there are different technologies here, like these diamonds. These are artificial diamonds. So don't cheer up. You're not going to get rich. They are very, very small. And they are quite interesting, actually, also, maybe even more than for quantum computers. They are used for quantum sensors. So what is the advantage is we can control them with photons. So basically we can send some information. It's like we can connect these diamond centers with photonic light, and then it's like we have a connected qubit. But they are difficult to produce and not really very much used nowadays. So quantum dots, topological qubits, they are very interesting. They are very stable, so there is no need for error correction. But this project is far away from really being in a something that we can exploit. So hopefully Microsoft is working on that so they can produce some results in the next years, so that because this can be really very this promising technology for universal quantum computers. And maybe the most technology which is used most of those here on this slide is trapped ions. So these are ions that we can keep in a vacuum, that we can control with lasers. We can move them. We can change their state. We can put them in superposition. That we can measure them. So yeah, it's quite interesting and very much used. But the most popular of all, they are superconducting qubits. So you see here how they look like. This here in the middle, we have a chip with 16 qubits. So these here small uh, um, things that you can see, they are qubits, and these wires, these are control wires. We can manipulate with them. You can put them in entanglement. We can read their state, etc. So um, if we zoom this really very much, then you will see this here important part, which is called Josephson junction, and all that looks like a circuit. It is a circuit. This is a superconducting circuit, and it becomes a superconductor when it's cooled to near absolute zero. So this is very important. Then when it's cooled to this temperature, then it's all this circuit where there is a they are the electrons circulating. So these electrons, they fuse together, and this becomes like a one system, one quantum system. And sometimes people call this artificial atoms. So they can be controlled, like sending some microwave pulses here. They can be, they are fixed, they are stable. So it's they are used very much. So this is the most popular actually technology now. It was just several, I think, a few weeks ago that IBM announced the new computer with 127 qubits. I have not seen what is the topology, so this is a great news, but still, I mean, still a bit far away from having a real fault-tolerant quantum computer. And there is also this photonic technology. It's very promising. That there is a lot of researchers, a lot of companies actually working on this. How does it work? Well, it uses photons, and photons, they are not like superconducting qubits. They are superconducting qubits. They are stationary, so they are always in the same place. Photons, they are flying, so and they are flying with the speed of light. So it's a completely different methodology how we exploit this light. So here you see how it works. The laser beams are entering this photonic computer. They're entering this squeezer, which introduces the entanglement. Then they're entering this linear interferometer. These are rotators, they are beam splitters. You see, these are hardware components, but they are programmable hardware components. And Xanadu, who is producing this computer, they provide also the programming framework, strawberry fields. And you can use these strawberry fields to code the parameters of these interferometer uh, splitters and rotators. So at the end, photons are coming to the photon detectors where they are counted, and we are getting, again, probability distribution. So this particular machine is called boson sampler. Well, why this is Gaussian boson sampler? Well, boson is just to say that this is light. Right? Boson fermions, they are just waves and particles. So bosons are light, and sampler is a machine that is creating probability distribution. So yeah, well, this is what it is doing. And Gaussian is because it produces normal or Gaussian probability distribution. So is this useful? Well, it turns out it is. Because many objects from networks to molecules can be modeled as graphs. And a graph can be very easily encoded into this Gaussian boson sampler. So we can code different use cases, like, for example, finding a subgraph, a dense subgraph within a graph. So these are the nodes of a graph that are interconnected, very much interconnected between themselves. And then we can also find what is the max click, for example, and this max click will help us uh, to understand the behavior of molecules. Um, yeah, so uh, this is one example of how photonic computers can be used for uh, network analysis, for uh, molecular analysis, like for chemistry, um, and they are quite promising because they can operate at uh, uh, the temperatures which are not close to absolute zero. So this is very interesting, and also they are easily scalable. So yes, a lot of people, they believe that once when this technology is mature enough, it can grow to easily to 1 million. We can just add more and more uh, of these um, photonic detectors and sources together and use these interferometers. So this is the world champion coming from China. As you remember, they have announced at the end of last year supremacy, well, with their photonic computer. So it was just last month that they have announced a new version of that computer. It's Zhejiang 2.0. With last time it was 73 photons detected. Now they have increased this with the new version of the computer to 113 photons. So quite exciting. They don't have this uh, coding framework, strawberry fields that one can use, because this is coming from a university. So it's for their researchers, and we'll see what will come next, if they will develop a software and how this will evolve. I think I should also mention a very interesting also project coming from European Union. This is focusing. This is from Italy. So this is a research team that is experimenting with, for example, um, three-dimensional hardware circuit, and also this linear interferometer. They have published a paper talking about introducing non-linearity into this boson sampler, into this interferometer, which can increase the expressive power of that photonic computer. So um, I mentioned noise. I mentioned that this is far away really from being fault tolerant. So what does it mean? So uh, all these computers nowadays, we are just calling them noisy intermediate stage quantum computers. Uh, and they have different issues. For example, quantum memory. We can't keep these states somewhere. So we just have to use them, and we have to measure very quickly, and we have to discard them. Uh, Maximal coherence time of the superconducting qubits is 1 millisecond. So, well, okay, gates, for example, single qubit gates, they can be done in just a few nanoseconds. So that's true, but multi-qubit gates, they take longer. So this 1 millisecond is not enough for really deep circuits. And there is a noise. This noise is actually coming here on the right-hand side. You see uh, what the different sources of noise we have and how it actually degrades our state. It should be 1, but after some time, after 40 instructions, it gets to 0. And it gets even, the opposite side. So it's really uh, a big problem. So how do we deal with this noise now? It's something which is called error mitigation. We need to model this noise. We have to create a noise model in order to cancel somehow this noise from the results that we are getting. It's like, for example, you have a headset, and then there is a noise cancellation. But it has to. It doesn't really cancel the noise which is coming from outside, but it is learning. Where is this noise, and can I somehow cancel it? Can I somehow uh, uh, I know what it is, so I want to exclude it. I want to recover somehow this initial state. It helps, but it doesn't really help if you have deep circuits. So that's not really possible to work with it. So the problem with really creating a fault-tolerant quantum computer is that error correction requires 10,000 qubits, physical qubits, for one high-quality qubit. So if you have 100,000 qubits, then and they are noisy, then you will need to use all of them just to have 10 high quality qubits. This is the problem. So even 1 million of qubits with photonic systems, and they also have problems with photons are different, then photons are being lost. There are some other sources of noise. So basically, that's what can really create the results that you don't expect and that are completely wrong. So what do we do then? Well, in meanwhile, we can use simulators. You can install one of those quantum coding frameworks on your laptop. You can simulate up to 20 qubits. It will work. There you don't have any noise, and you can use it to learn. You can use it to prototype, to work on some small scale problems. Then uh, if you want more, then you can create some kind of corporate server. There is also this company Atos. They are selling this learning machine, Atos learning machine. This is a specialized device that you can. They have. It comes with their own programming framework. It's tuned for the best performance. So if you want to simulate 50 qubits, then well, that's because of that superposition can keep much more states than normal memory. So you will need much more qubits there. So I wanted also to mention here this Fujitsu digital annealer. So I mentioned the D-Wave annealer, and this Fujitsu digital annealer, it's not really, it doesn't use any quantum cube systems. It's just a regular computer which is simulating the behavior. So having in mind the progress, it is great, but it's not enough. And we are far away really from having fault-tolerant quantum computer. It's very difficult to forecast when this will arrive. So there are some people, they are optimistic, there are some pessimistic. I don't know if I have to put some numbers here, then I just decide to put a range of 15 to 30 years from now. What are the programming frameworks? How do you code? So the most popular, maybe the most famous of all is this Qiskit. It's coming with some low-level instructions, but also with high level for quantum chemistry, for machine learning. There is a large community around it. And it works actually, it's based on Python. So Google is producing Cirq and TensorFlow Quantum. So TensorFlow Quantum is for people who know TensorFlow, so they can integrate quantum instructions with TensorFlow. Q Sharp by Microsoft. I have a friend, he really likes this Q Sharp. He says this is Microsoft is a company that knows how to develop software, and this Q Sharp can really be used to develop productive software. So you can use Visual Studio to develop these codes. And I mentioned Strawberry Fields. There is also Penny Lane. Penny Lane is another framework produced by the same company. This is specialized for machine learning. So it's something that can be used for artificial intelligence, machine learning. So I wanted also to highlight here two projects. This is Project U from Switzerland. This is a very interesting project because it optimizes, it uses machine learning, it optimizes your code, and it can run on different backend devices. For example, if you want to work on IonQ, IonQ recommends using Project Q for coding your scripts. There is also Quantastica Q Convert.
Hi, Sasha. I'm really sorry to kind of have to cut you short like this, but we've already cut into some time. The speaker for the next talk was a bit late, so we let you continue. But it's really time for his talk. I'm sorry for. Can you maybe say a few final things, and then we can move on.
Okay, so I will skip all this. So just I want to say, if you want to learn what you should do, so there are a couple of books here that I can recommend. Quantum. If you want a traditional approach, for example, you can just go through this large book of 700 pages. Qiskit textbook is agile. It's you start coding, then you go back and you learn a bit theory, and then it's more interesting. So there are different courses here, online courses. I recommend this here. They are quite interesting. And if your organization, your team would like to learn more
Yeah,
about
of
this
course.
quantum computing,
We will be forwarding them your presentation after we finish with the conference in maybe a week or two,
yep.
and they will have access to it. So thank you
Okay.
very much, Sasha. I'm sorry to have. I see that it's a very interesting topic that you might have a lot of time to kind of talk about it, but unfortunately this format kind of doesn't give us that room.
Yeah, for those who would like to continue a discussion, please contact me here. There is my contact details.
Okay.
And
Uh, Thank you again. See you.
yep, thank you.
Stay here, and we are continuing with the next talk immediately after a short commercial.